Now we'll see how to use Gaussian elimination to solve a system of equations. The key idea is to keep track of the transformations performed in converting a matrix to echelon form. The algorithm actually computes matrices M and U such that M times A is U, where U is in echelon form and M is an invertible matrix. Let's see how we can use this to solve a matrix vector equation AX equal B. First, we compute M and U such that M times A equals U. Next, we compute the matrix vector product M times B and use that as the right-hand side for another matrix vector equation, UX times MB. Let's see why this gives us the solution to the original matrix vector equation. Well, suppose V is a solution to this equation. So U times V equals M times B. Now, M is an invertible matrix. Here's its inverse. Multiply both sides of this equation by M inverse. Now use associativity to reorganize it. And notice that M inverse times M is the identity matrix. And use the fact that M inverse times U equals A. This shows that A times V equals the identity matrix times B, which is B. But why is this matrix vector equation any easier than the original one? Well, if U is triangular, then we can solve it using back substitution. And more generally, U is in echelon form, and we can use a similar algorithm. Now let's see how we can use Gaussian elimination to find the null space of a matrix. Well, in fact, we're going to find, given a matrix A, we're going to find the set of vectors U such that U times A is the zero vector, which is actually the null space of A transpose. But of course, you can use this algorithm on the transpose of the matrix. Let's say this is the input matrix. So we find matrices M and U such that M times A equals U, and U is in echelon form, and M is invertible. Here's the solution to that. Now notice that the last two rows of U are zero vectors. Now, row 3 of U is obtained by multiplying row 3 of M by A. And row 4 of U is obtained by multiplying row 4 of M times A. So we've identified two vectors, U, such that U times A is the zero vector, namely rows 3 and 4 of M. Do these vectors form a basis for this space? Well, the dimension of the row space of A is 3. We already know that the non-zero rows of U form a basis for the row space of A. Since there are 3 non-zero rows, that shows that the dimension of the row space of A is 3. By the rank nullity theorem, the dimension of the row space of A plus the dimension of the null space of A transpose equals the number of rows, which is 5. So that shows that the dimension of the null space of A transpose is 2. Now, since M is invertible, all its rows are linearly independent. Therefore, in particular, rows 3 and 4 of M are linearly independent. So they span a space of dimension 2. Since these vectors are in this space and have the same dimension as this space, they are a basis for that space. Now let's see what it means to record the transformations. Let's recall how Gaussian elimination works. You start with a matrix, and you start performing these operations, these elementary row addition operations on the matrix to change the matrix. Eventually, the rows of the matrix can be reordered to get a matrix in echelon form. We're going to keep track of those transformations. So we start with this matrix, and initially, this matrix is the same. Now, at some point, the algorithm performs an elementary row addition operation, adding some multiple of one row to another. We represent that by a matrix multiply, where this matrix is an elementary row addition operation. Say the algorithm performs another elementary row addition operation. We represent that by multiplying by another matrix. all the time this right-hand side matrix is being transformed. This is the current state of the matrix after those transformations have taken place. So now we do another transformation. However, it's going to be too cumbersome to keep track of all these elementary row addition matrices. So we'll see there's a shortcut. Let's do a concrete example. We start with this matrix, and on the right is the same matrix, because we haven't carried out any transformations yet. In the first step of the algorithm, we perform an elementary row addition operation. We subtract 2 times the second row from the third row. And this is the result. Next, we do another elementary row addition operation. We subtract 2.5 times the second row from the fourth row. And this is the resulting matrix. Now, these two transformations can be combined to make a single transformation just by multiplying them together. Now we can continue. We carry out another transformation represented by this matrix in which we add half the first row to the third row. And this is what we get. We again reduce the number of matrices here by combining them. Here's how we record the transformations. We maintain a matrix M, which is initially the identity matrix, and a matrix U, which is originally the input matrix A. And whatever transformations you do to A to move it towards echelon form, you do the same transformations to M. So let's go through Gaussian elimination. We start with this equation. Here's the matrix M. This is initially identity. Here's the original matrix that we're going to transform, and here's the matrix we're going to put into echelon form. We go through the columns of this matrix one by one. Let's start with column A. For that, we select row 1 as the pivot row. And we add it to rows 2 and 3 in order to zero out those entries. So here's what we get. The entries have been zeroed out, and we're done with row 1. Next, we move on to column B. For this, we select as our pivot row, row 3. We add it to no rows because all the other entries in row B are already 0. Next, we go to column C, and we select as our pivot row, row 0. We add it to row 2 to zero out that entry, and we get this matrix. Finally, we consider column D. We select as the pivot row, row 2, and we don't have to add it to anything because there aren't any rows left. So we're done. Now I'll give you the code for carrying out that process. As before, we initialize row list to be the list of rows of A, and we initialize M row list to be the list of rows of the identity matrix. Then we carry out the iteration. Here are the differences from the previous code. Every time we choose a pivot row, we append to new M row list the corresponding row of M. And then when we do an operation that adds a multiple of some row to another row, we do the same operation on the matrix M, represented by M row list. Now we've been appending the pivot rows to new M row list. So that takes care of all the rows of M in order that correspond to pivot rows. But at the end, there are some other rows that never get chosen as pivot rows. They're the ones that correspond to 0 rows in the echelon form that we create. So we have this loop at the end to just add those remaining rows to new M row list. That will ensure that new M row list times the original matrix will give us the whole matrix in echelon form, including the 0 vectors. And finally, at the end, the procedure will form a matrix M from row list and return that. We provided that code in the module echelon. Okay. So with Gaussian elimination, the black box has started to become less opaque. We're starting to figure out what's inside it. In particular, both the module's independence and solver use Gaussian elimination in dealing with matrices and vectors over GF2. So the procedure solve AB computes this matrix M such that M times A is in echelon form, and then uses M to try to find a solution, as we described earlier. The procedure rank, defined in the module independence, converts a matrix to echelon form and then counts up the vectors that are non-zero. That tells you the rank of the matrix in echelon form, and therefore also the rank of the original matrix formed by the vectors in L. We also saw that Gaussian elimination can be used to find non-zero vectors, in fact a basis for the null space of a matrix, and you'll use that in an algorithm for integer factoring.